The topic, Boyer-Moore algorithm for string matching problem. We did this before. So remember, we did this when we studied the topic brute force and exhaustive search. So we used a very simple method to solve it. So we revisit this problem. Just remind you the problem. So we're given n characters text and m character pattern. Then we're trying to find a match. All right, so that's the, that string matching problem. We got result, our old result, worst case efficiency, m times parenthesis n minus m plus 1. Yeah, so very easy. But we are not satisfied with this solution, so we want to improve it. Yeah. So the question, how do we improve it? So what is the main idea to improve it? Yeah. So here, the reason the old method not very good, not quite efficient, is every time when we shift our pattern to the right, the shift size is too small. Every time we only move one character to the right, that is not efficient. Okay, so we compare the old way, new way. The old way, every time move one character to the right. That is too slow, one character. Is it possible we can move faster than that? So for the new way, we want to do faster than that. We want to increase the step size. So we need to do some work to tell us when we move faster, we have no problem. So we will not miss any possible matching substring. Yeah. Otherwise, if we miss some solution, so that's too bad. So that's the reason we need to do some work. Yeah. All right. Next, the method, input enhancement method. Look at this, input enhancement. So this enhancement, we need to do some work on our input to enhance, to collect more information, to make us make a better decision. So that's the meaning of the enhancement. Yeah. All right. So now, the question is, how do we do that input enhancement? Yeah. In the old method, we did not consider any property in the pattern. Yeah. So we didn't use any information from the pattern in our old solution. So that's the reason we cannot move faster than one character step size. So if we can explore the pattern, extract more useful information, then we can make our step size larger. Yeah, so that's the basic idea. Yeah. So let us make some assumption, assumption matching the real world situation. Yeah. First, the number of characters in the pattern is a relatively small number. Yeah. Search keywords in a document. The keywords usually contain relatively small number of characters, right? So that's really, this observation comes from real-world experience. Yeah. Second, the number of characters in the text is a much larger number comparing to the number of characters in a keyword or multiple keywords. Yeah, so that difference is very big. Yeah. So that's our assumption. Yeah. All right. Now, based on this assumption, what is our conclusion? So what step can we take to take advantage of this assumption? Yeah. So the step we can take, process the whole pattern, because a small number of characters, so we can process it. We can try to, study the information really well, so then we can apply that knowledge to our string matching. Yeah. Yeah. The cost will not be that high if we do that. Yeah. So do initial investment with relatively low cost. That's our initial investment. Yeah. If we pay, we need to pay the cost. Yeah, but that cost is relatively small. Then after that, later, we can get much more back. Okay, yeah. So that's the basic idea. All right, so in the text processing, reduce the cost with a pre-computed, here we use this word, pre-computed information. We do pre-computation. Pre-computed information. Yeah. So here you can see our new idea, doing pre-computation. So this word, similar to that input enhancement phrase, yeah, but actually this name is more general than that input enhancement, more general. And actually, we can use this pre-computation idea in many different situations. Yeah. Here, let me give you a well-known example. Google search engine. Google search engine. This example. In Google search engine, people do pre-computation. That's very important. Think about when you type keywords in the search fields. After you click the search button, then the engine starts the search. Is it possible the engine can search the real-world documents and find a match? It won't be possible because it will be too slow. There are billions of web pages in the real world. There is no chance any engine can find a quick match in a fraction of seconds. So how to speed up significantly? The basic idea is pre-computation. So how to do that? So there is a step called indexing. So in Google, the pre-computation is doing indexing. All right. Before you click search the button, so in the Google servers, they do indexing first. They send very special small web programs to the world to visit all the web pages in the world. So they call it spider. So crawling, right? Spider. Yeah. So they visit, so they do the indexing. So when they get one web page They process based on the keywords. Then they do indexing. They store keyword document matching in the database. So they build a huge database doing the mapping. One keyword corresponds to several documents. Okay? Yeah. Many web pages. Yeah. So they have that data already built in their database. So that is the pre-computation. All right. Now, when you hit the button, so they do not do the global search, they just search their database. So this keyword, how many pages contain this keyword? So they return that information. So that you can see, multiple millions match containing this keyword. First, you get that information from the database. Second, they only need to send the first top page, the first page to it. The first page, small number of web pages, the links, they only need to send you the first page. So that's also very fast. So that's why you get a very fast response. But the engine does not do real-time search. The engine goes to the database to extract, to retrieve the match information. Yeah. So now you can see the power of the pre-computation. Yeah. That's a simple example. Yeah. All right, so here we do the similar pre-computation. All right. Construct pre-computed table. Yeah. So we need to, collect useful information, pre-computed table. Yeah. So what information do we compute for the table? Okay. All right. Related to the step size, right? Because we want to know the step size. So that's the main information. Yeah. Here we also call the shift size. So each step, how many characters do we want to shift the pattern to the right? The shift size. Okay, yeah. For each character, yeah, so each character, there is a shift size. But when we go to the different character, the shift size could be different. Yeah. But which character? So later you will see. Yeah. So the character, suppose this is the pattern. Okay. We try to match the one, because we compare in this direction. Okay. So not from right to left, not from left to right. Okay. Yeah. Right to left, the first character, yeah. When you look at that, if different, right? Different, that means we need to shift. So now when you shift, here there is a character, right? So this character corresponds to certain number of characters as the shift size. That's the meaning. Okay, so this character, there is one shift size corresponds to it, so we need to calculate that information. Yeah. All right. Okay. The minimum shift size is 1. The maximum shift size is n. Yeah. And for the general case, we get an integer between these two numbers. Yeah. Could be any integer between these two numbers. Yeah. But the larger the shift size, the faster our algorithm. Right? So if we can move the pattern faster, then we can complete the search faster. Yeah. All right. Now, so let's do some analysis. Yeah. Suppose this is the text. Then we have a pattern. Yeah. In the middle part of this text, so we compare the first character C with the first character in the pattern from the right. There are two cases. The first case, C is not in the pattern. Not in the pattern. So you cannot find a C character in the whole pattern. Okay? So then this tells us do not try to match anything in the middle to that C. So no character in the middle of the pattern can match that C. Then our shift size is very easy. The largest possible shift size. Here I use this SSZ represent the shift size. The shift size this time is M. Okay, so that means we shift the whole pattern to M characters to the right. Then start comparison again. Yeah. All right. Then another situation. This time, this D, the next time we compare the first character for the comparison, this D is contained in the pattern. Where it is contained in the pattern, so we can find a match somewhere in the middle, right? So then this time we need to shift, this smaller number, yeah. So for this case, actually, we need to do some more discussion. Yeah. The first case, very easy. Yeah. So we're done. But the second case, we need to do more discussion. Okay, yeah. All right. So same or not? Not, we know M, right? So the main discussion is about the same case. Yeah. All right. Now let's look at the case. Yeah. Let's assume D is in the pattern. Yeah. All right. But if D is in the pattern, yeah. Right. Yeah. So case one, D is different from the last character of the pattern. Yeah. So D is different. Then this D could have multiple. Could have multiple occurrences. Multiple occurrences, right? Yeah. So we need to look at those occurrences. Yeah. All right, so look at this situation. Yeah. But when we consider the shift size, we should use the rightmost occurrence of D. Yeah. Other than the first one. The first one the same, right? The first one, but we do not count this one. Okay? Yeah. The rightmost occurrence before the first character in the right. Yeah. Then we align these two characters and do the comparison. Okay? Yeah. So that's the basic idea for the case one. Yeah. All right. In this way, you can see we determine the shift size as this number. Yeah. The shift size can be determined in this way. Yeah. All right. Case two. D is the same as the last character. Yeah. D should be the same character. Right. All right. So this case. Yeah. But all right. So now, yeah, we just try to go. D is not in the pattern from 1 through the M minus 1, not including the last one. Okay, the D is not there. Yeah. If D is not in that pattern part, then we know the shift size. If D is in that part, then we have another shift size. Yeah. All right. So here we assume the last character matching. Yeah. Case 2A. D is not in this pattern from 1 through the n-1, not including the last character. Okay, not there. Not there, that means you don't need to try to match anyone in the pattern with that D. Okay, yeah. Your shift size could be not matching for the pattern, right? So here, yes. All right, so let me try to get it straight. Yeah. All right. This condition, not matching for the pattern condition. We need this condition. So what's that? All right. The situation like that. Let me repeat. Yeah. All right. D and this character the same. All right. Yeah. So that's the first condition. Otherwise, so we did before. So this D and this same. Second, then we need to compare the second. Are they the same? If they are the same, third and fourth will keep comparison, but at one step we find not equal. Okay? At one step we find not equal, then we have this condition, no matching for the pattern. Alright? So then we have no matching for the pattern. Then we check, is D contained in the pattern from 1 through n-1 position? Yeah. That's our 2A case. Okay? That's our 2A case. Yeah. So that's the whole background. All right. In that case, our step size equals n. All right, that's the 2A. Okay. 2B, all right, still no matching for the pattern. That condition is satisfied, but D is in the pattern from 1 through n-1. Okay, if that happens, now we align to rightmost occurrence of D in the pattern. Yeah, rightmost occurrence, that one. Yeah. So there is a certain shift size we need to, yeah, because there is occurrence. So we get the first occurrence. So that is the shift size. Okay? Yeah. So we can calculate the distance. The distance from the rightmost occurrence of D in this pattern part from 1 through n-1 to the last character. So that distance is our shift size. All right. So that's the meaning. Yeah. For case 2. All right. Yeah. So we complete the first part. The second part, we will use an example to explain the algorithm. Yeah. But we still have some more work to describe the shift size. Here, the key idea is the shift size. Yeah, it is not that easy to understand. All right, so let's look at the last part, B.5 of this class.